Right, so atomic theory notes, part 2. So guys, what we were talking about yesterday were electrons, and we were talking about how they act as a particle and as a wave, and there's some math that goes into it to figure out the energy that's released from an electron as it goes from a higher state to a lower state. All right, so moving on to electron placement. Where are electrons? Well, the Heisenberg uncertainty principle says we cannot be certain where an electron is. We can only have an idea of a zone of probability of where it could be, kind of a room, so to speak, of where it can be. And that's only true even 90% of the time, so it's not even always true. And in the Bohr model, we use, when we're talking about energies and difference in quantums, or levels, away from the nucleus. So as well as in quantum mechanical model, there's still a probability electrons can be found in the nucleus of an atom, which is kind of trippy. We don't think of electrons in the nucleus, but it's not beyond it. All right, we got sublevels, and levels are spoken to in terms of n equals 1, n equals 2, n equals 3, and so on. They also refer to shape of an orbital in space. They can be S, P, D, or F. Those are the ones we're going to focus on. We have, okay, we don't. So the S is a spherical shape, so that's a sphere. We'll shade it. That's the shape of the zone of probability where those electrons can be found. So S starts when n equals 1. And I'll show we got a little Bohr model. N equals 1. And then the next shape is how's that work? This is the P. So those are supposed to be bow ties. That's a terrible bow tie, sorry. Yeah, kind of like the infinity sign. You got it. So these are basically like two balloons together, one down and one up. That's the bow tie shape, the zone of probability of where these electrons can be found. And each shape can have a max of 2 electrons. So max of 2 electrons, 2 electrons, 2 electrons, 2 electrons. So the p orbital has actually like 3 different sub-levels, sub-shapes, each of them having a max of 2 electrons. So p could have overall 6 electrons. If we switch to the orbital filling diagram, S is represented by, sorry, this is IB, so we got to go with circles. If it's AP, it's box. So, but IB likes circles. It's an up arrow and a down arrow. Means that you have 2 electrons in this S orbital. If you have just one up arrow, you just have 1 electron. If you have no arrows, it means it's empty. And then the P is represented by 3 circles close together. And you can have a max of 1, 2, 3, 4, 5, 6. Speaking of that, I want to just get to Hoons' rule right down here. So Hoons' rule says that each electron has to be, or each suborbital has to be filled with at least 1 electron before you can pair them up. So you've got, let's say you got 4. You don't want to do that. This is excited state. I mean, can that occur? Yes, excited. So I'd want to fill each one up, 1, 2, 3, 4. Electrons are like really sloppy roommates, so they don't want to be roommates with each other. So, unless they have to. So this is the ground state, or low energy state. Both have 4 electrons, but this is, according to Hoons' rule, what it does naturally, lowest energy. You guys need this now.
We did this in prep chem, right?
Yep.
Okay.
Prep chem. Yeah, this is all review, this type of stuff.
How would they get excited?
Excited just by increasing energy, like an electric current. So in sophomore chemistry, you guys had these spectroscopes, these tubes of gases, and when you turned on the light switch, it injected an electric current or energy into it, exciting the electrons. But then as quickly as they got excited, they're going to go back to their ground state right away. And when they do that, they release energy in the form of light, and that's what we see.
Is that also why metal glows red?
Why metal? Part of it, yeah. So, yeah, because they're going to have similar electron arrangements, and not all metals are going to glow the same tint of red or color. All right. So next we have the SP, and then there's the D. We're going to need a lot of paper for this. The D is like a flower petal, but it's three-dimensional and looks prettier than that. Thing about this is there's 1, 2, 3, 4, 5, and then you got that bizarre dumbbell in a donut shape. We got 1, 2, 3, 4, 5. Each suborbital has 2 electrons max, with a total of 2, 4, 6, 8, 10 possible electrons that could be in the d orbital. So we would draw this with 1, 2, 3, 4, 5 circles. If you're doing the orbital filling diagram representation of the arrangement of electrons. All right, and then the f orbital, we don't get into the zone of probability or the shape of that one. It gets more complex, and so at this level we represent it with circles only. So this is S, this is P, this is D, and then F would be 1, 2, any guesses? 1, 3, 5, 7. 1, 2, 3, 4, 5, 6, 7. So these would have a max of 14 electrons. And IB is not concerned with knowing the shape of the zone of probability for those. Actually, they don't really get into the quantum numbers too much, where n equals 1, L equals 3. So it's not going to be on your unit assessment. It won't be on the final exam in May, but it is in the reading of Zoomdal, and I'm offering formative bonus if you do that. You read that portion and do that. I have it on Canvas. Which questions? I think it's 3 questions, like 71-ish, somewhere around there. So, but I'm not going to focus too much on it because you don't even know it. All right. Yeah.
So is that what like this shape is showing here? This is on like ptable.com.
P-table, that's oxygen. Yeah, there is a spot where it shows.
Is this the shape of like the orbitals? Or no?
Oh, that's
yeah. So
which setting is it in?
it's on electrons. Because I just keep seeing those shapes and I was wondering.
Yes, that is it.
Okay,
for sure.
Okay, sweet.
Yep.
Thanks.
No problem. All right. Moving on to Pauli exclusion principle, offball principle. We already talked about Hoons' rule. Pauli exclusion principle is even more important. It says that you can have no more than 2 electrons in the same suborbital, which is why right here 2 is the max, 2 is the max, 2 is the max. And that's because one electron is going clockwise and the other is going counterclockwise. They do that because it's lowest energy. Because how many times do they see each other? Once, twice, 2 times per rotation. But if they're going parallel, then they're seeing each other like infinite amount of time.
Whoa.
Oh no, not. There we go.
Yeah, like what? I got
It's
it.
like doing that.
You go one
There we go. Lydia did it. You got a slow version of it.
Really?
Yeah. Oh no, you lost it. Because electrons are negatively charged and they repel, they want to be seeing each other. So 2 times the rotation is the minimum amount that they can see each other.
He does it so easily. What?
The other one is offball principle. Offball is German for building up. And so you got to start from close to the nucleus first to further out from the nucleus. You always build the first floor before you build the 13th floor. It's just kind of how it works. Same thing with electrons. So, let's do a quick little example right here. Can we have an electron right there in energy level 2? No, it's not going to happen unless it's excited. But if it's at its ground state, it's going to have to be it's going to have to start at the ground state, which is n equals 1, or the 1s electron configuration. That's what offball principle is saying. So all of these 3 principles or rules lend themselves to showing how our electrons are arranged in an atom. And this is all supported through mathematics and high-level physics and fancy experimentation that we don't have to worry about. So we just have to trust them that, okay, that's how it is. All right. Hey, speaking of arrangement of electrons in an atom, I think the next thing it says, examples of electron configuration and orbital filling diagrams. All right, nice. So let's start simple. Hydrogen.
S1.
Close. 1s.
1S.
1, yeah. So hydrogen, so periodic table.
Right there.
It is, but I want to get on video. It looks like one of my irresponsible chemistry. Oh, here's one. There we go. Oh, man. Don't know what that. All right, so
You said it so seriously, though.
what we got right here, hydrogen's in the first row, so that's going to be relating to the first energy level. So we call it 1, and we use the periodic table to kind of help relate it to the electron arrangement, to kind of help us visualize it. But the first 2 columns, the electrons that form, the last 2 electrons basically in an element are going to be in the S, or in this case the first 2 electrons. So this is S, because hydrogen's in S, and we have just 1 electron, so we write a 1. That's the electron configuration for hydrogen. So let's do something a little bit harder, like sodium. All right, let's move right to sodium. So you start offball principle, ground up, first energy level, 1. It's in the S. So we got 1, 2. Even though this is the P section, it's lumped with the S. So, and S has a max of 2 electrons. You can't put 3 in there. It overflows the bucket and it doesn't fit. So you got to go to the next thing. So the third element, this is the second row. And if we're relating it to the orbital, not the orbital, but the Bohr model, we got 2 electrons, and then we're in the second energy level now. That's kind of another way of representing it. Hey, this is in the S section, so it's going to be 2S. 1, 2. Can I have more than 2 for the S? No. That fills up the bucket. So I got to get a new bucket. But I'm looking for sodium, so I keep on going on to boron. Is this still in the second row?
Yeah.
Yes. Yeah. Second row. But now, all of these are considered P. So these are in the P orbital. And we've got 1, 2, 3, 4, 5, 6. The nice thing about P is it can have up to 6. And it gets filled up. And then we go to sodium, which is in the 1, 2, 3rd row. But it's in the S section again. And it's 3S. And 1 will get us to sodium. And there it is. 1s2, 2s2, 2p6, 3s.
What was the way you can break it up? So instead of going from P to Li, you can start writing it.
Oh, so if you want to go right to the shorthand, all right.
Yeah.
So you can do noble gas shorthand. First of all, take a step back. These are the S. these are the P, these are the D, and the bottom two rows are the F. Those are the F. All right, so noble gas shorthand. What you can do is go to number 11. Which noble gas comes right before number 11? Neon. So we could do neon in brackets, and then continue on. Instead of starting at hydrogen, we're starting at neon. And we're going to number 11, which is the third row, S section, and 1.
Oh, that's nice.
That makes it way easier. Because the next example I was going to do was radon. No. Well, yeah, let's do radon. All right. Is that
Okay,
radon?
so let's
All right. Let's not start at hydrogen. No. Okay. So if you haven't... Oh, okay. I'll keep this in suspense for you guys, and we'll continue
Wait,
this
should we do XE?
tomorrow. You start with XE, and then continue on.
XE